Hello, today we're going to cover solutions by substitution. So we have three different substitution methods to cover for first order differential equations. One thing for you to work on though is always, as we learn new methods, go back and refresh your memory on what we have already learned. So we've learned three different methods and they cover the situations where our differential equations are separable, linear, or exact. And those are the only three methods we've learned. And when we cover these next three substitution methods, we will be finished with the first order methods for solving differential equations. Now, if our differential equation does not fall into the separable, linear, or exact, that's when we want to start asking ourselves, well, would a substitution work? Okay. And if a substitution doesn't work, then, well, we'll have to approximate a solution. And that's what the last section of chapter 2 is going to be about. We'll get there. The first substitution method is dealing with the homogeneous differential equation. And the idea with a homogeneous equation is that our equation will look like it might be an exact equation, but if we were to do an exactness test on it, it would totally fail. Okay, so it'll fail the exactness test, even though it looks like it could possibly be an exact equation. And we won't be able to find some integrating factor for two reasons. One, we didn't cover it, so we don't know how, but two, because there will be no way to actually force it to be an exact equation. So what we need to do is we need to be able to check the m of xy and the n of xy to see if they are homogeneous equations. And the point of a homogeneous equation is that if you were to put in some substitution of some sort, you would change your whole equation into a separable equation. That's it. That's the goal. Okay. And so that's kind of what this property right here is saying. It's saying if we take a function and instead of everywhere there's an x, we just have x, we're going to replace it with tx. And everywhere there's a y, we'll replace it with a ty. And the hope is that after some algebraic manipulation, we could factor a power of t out of the equation and leave behind the original f of xy. This right here is exactly showing that there's like a separableness to this problem now. Now, let's just see what that looks like. We're not working with homogeneous equations yet. We just want to know, how do we check to see that our function is homogeneous? And how would we know that it's not homogeneous? Okay, so in the first example, we let f of xy equal y squared plus xy. We want to know, is f of xy homogeneous? Well, the way to answer that question is to plug in tx everywhere there's an x and ty everywhere there's a y. So we do that. When we plug things in, the y squared becomes, in parentheses, ty all squared plus x becomes tx and y becomes ty. And then we simplify that and do the math. It becomes a t squared y squared is equal to t squared xy. Now I'm noticing a t squared common to both terms, and that I also have too many equal signs. That should have been a plus. Okay, so I can factor out the t squared, and that leaves behind a y squared plus xy. But that was the original function. F of xy is y squared plus xy. So what happened is now I've got t squared f of xy. And because I put in a substitution and I got back something where all the t's were separate from the x's and y's, I can now say that f of xy is homogeneous. So the math isn't typically too hard. It's, some basic algebra, but every now and then it can be a little bit tedious. Now let's see what happens in the second one. Let f of xy equal y plus e to the x times y squared. Is f of xy homogeneous? Well, let's look at it. F of tx ty will give us ty plus e to the tx times a ty in parentheses getting squared. Let's simplify this. It becomes ty plus e to the tx t squared y squared. And I see the only thing in common with the two terms is a t, so I factor that out. The t leaves behind, after it's factored out, a y, plus it looks like a y squared t e to the tx. And what that's showing me is that I didn't get back some power of t times my original function. So this does not equal t times f of xy. It left behind something that is totally not separable. And that means that f of xy in this problem is not homogeneous. So this method that we're about to learn would not work for this equation. Okay? So now if we know that our m and our n are homogeneous, then we need to know what the substitution is that we would put into our differential equation in order to make it something we can work with. We have choices. And I will tell you right off the bat, I always use the first choice. And if it doesn't work, that is the only time I would go to the second choice. But either one of them should work. When I say that I use the first choice unless it doesn't work, what I mean by that is I use the first choice unless it's so ugly that I don't want to work with it. That's more like what happens. Okay, so the first choice is that in part A, we could let y equal u times x, and then we would take a total derivative on that, and so that'll give us differentials, and we would get the differential dy is equal to u dx plus x du, or we could use the substitution x is equal to vy, and then dx, the differential, would be equal to v dy plus y dv. So the nice thing is we get to choose. The hard thing is making a decision. And that's going to be, kind of up to you. You'll see what I do through these problems, and then hopefully you work through some problems and develop which choice you like best or how you decide which one is best for you. Step 3, once we have substituted one of the above substitutions into our differential equation, then our differential equation will be separable. And that is what you have to remember, okay? So let's put this in here. This is like in bold. Okay. Homogeneous equations become separable equations. After the substitution. Okay? And it's important to know where your differential equation goes with each substitution because it's different depending on the substitution. So if you're looking at a homogeneous equation and you do the substitution and you're trying to make it look like a linear equation, you're going to make your life much harder on yourself, right? So that's the part you really want to remember, okay? Now, solve the given homogeneous differential equation. Now, my practice, what I do is I always split up my differential, the dy and the dx, because I already know that this is working towards a separable differential equation. I don't want to work with dy dx together and substitutions because it gets a little ugly, okay? I'm not saying my way is the only way to go, but it's the way that I practice these. So first things first, I'm going to clear by multiplying both sides by dx, and I get xy squared dy equals, in parentheses, y cubed minus x cubed times dx. Then, I already said it earlier, I'll say it again, I always just use the first substitution. Now, one thing I want you to remember is whether we use y equals ux or x equals vy, the u and the v don't really matter. They just needs to be some other letter. Okay, we could use y equals tx. We could use y equals vx and x equals uy. It does not matter. The point is, what we're substituting in is what is proper for a homogeneous equation. We're letting one of the variables be a variable multiple of the other variable. That's kind of weird to say. Let's try it. Okay, so I'm going to use the substitution y is equal to ux. And if I run a differential through this, I get dy is the derivative of u within the, like, I'm taking the differential. So the differential of u is just a du. So I can get an x du plus the differential of x is just a dx. So I get a u dx. So I'm just using the product rule there with the differential. And notice that mine is in the opposite order of how I have it typed up above. That's fine. Addition is commutative. No problems there. So I go ahead and I substitute everything in. Now, x's get to remain x's. Y's all become ux. So when I substitute in, I get x, and then in parentheses, ux all squared. dy is replaced with x du plus u dx with parentheses around it. If you drop those parentheses, this is not going to work. Okay? Gotta have them. This is equal to, in parentheses, y cubed will get replaced with u cubed, x cubed, then minus x cubed, close the parentheses, dx. Okay, so I very carefully put everything in. Now, on the left-hand side and on the right-hand side, I'm going to distribute the dx's, okay? And the dy, yeah, the du's and the dx's. I'm going to multiply everything out so that I can see all my individual terms and collect like things, okay? On the left, I have, I've got that ux all squared and then an x outside of that. That becomes a u squared x cubed times x du plus u dx. I'll distribute it in the next step. This is equal to u cubed x cubed dx minus x cubed dx. On the left-hand side, I have u squared x to the fourth du plus u cubed x cubed dx is equal to u cubed x cubed dx minus x cubed dx. Okay, so now at this point, what I want to notice is that I have on the left and the right a u cubed x cubed dx. They have the same sign, and this is where you need to be very careful. They have the same sign, so if I was to try to combine them by moving one of them over to the other side, they would be gone. I would be subtracting from both sides, so they would be gone. Okay, so what I'm left with is u squared x to the fourth du is equal to minus x cubed dx. And this right here is just about where I want to get to. I'm noticing I have a differential du on the left, so I want only u stuff on the left. On the right, I have a dx, so I want all the x stuff on the right. In order to do this, I just need to divide both sides by an x to the fourth. So when I do that, the left-hand side becomes u squared du. The right-hand side becomes 1 over x dx. And now I am in separable equation land, right? So at this point, I can go ahead and slap on some integral symbols. I have my differentials. Those were already there. That's the only thing that allows me to integrate with respect to different variables on each side. And so I go ahead and integrate. On the left, I get a 1/3 u cubed when I integrate u squared. On the right, the antiderivative of negative 1 over x is negative natural log of the absolute value of x plus c. Next step, I multiply everything by a 3, and u cubed is equal to negative 3 ln of the absolute value of x plus c. And I leave it as c because 3 times c is still just c. Okay, so I don't have to worry about that one. The next thing that I need to do is I need to get back in y and x. Right now I'm in u and x. I need to recall that y was equal to ux. Okay, so we'll do a recall. Y was equal to ux, and that means that u is equal to y over x. And so that u cubed needs to now become y over x. Okay? So if u is equal to y over x, we're going to substitute that into our u cubed. And what happens is we get y cubed over x cubed is equal to minus 3 natural log of the absolute value of x plus c. And now we would isolate the y cubed so that y cubed is minus 3x cubed natural log of the absolute value of x plus cx cubed. Now this time when I multiplied the c by something, that something was a variable. So it doesn't just become plus c anymore. Now it's c times the variable x cubed. The last thing that I could do is take the cube root of both sides. However, if I go back to the instructions, it just says solve. It doesn't say find an explicit solution. Okay, so that's really important. There was no request for an explicit solution, so I am going to call myself done right there. All right. So this is a homogeneous equation method, and I want to now redo this problem. And I know that seems like extra work, and it is, but the reason I want to redo this problem is I want you to see it with the other substitution. See what happens if we use the substitution x is equal to vy. Okay, so I'm going to shrink some stuff up a little bit here and give myself more room because I have already worked through these problems and I already know that the other way is kind of messy. And it's one of those ways I don't actually like to work with, but it is what it is. So we're going to do it. Okay. So I'll just put some little instructions here so that it's clear where we go from one step to the next step in these columns. Okay. Use a different color. Now we're going to use the substitution. X is equal to Vy. And with that substitution, I need a differential as well. So taking the differential, d of x is just dx is equal to, d of the first will be dv, so I get y dv, plus d of the second will give me dy, so I get v dy. Okay, these are my substitutions that I will plug in. So let me just label this. This is just to see the other way, okay? This is not something you also need to do. This is so you see both ways. Okay, go ahead and put my substitution. And I already have that form up above over here that I'm going to substitute everything into. So everywhere there's an x, I will replace it, with a vy. And everywhere there is a dx, I'll replace it with y dv plus v dy. Okay. So the x, y squared, the x is just going to be vy, and then times the y squared dy. This is equal to, in parentheses, y cubed minus the x cubed, which becomes v cubed y cubed, all times dx, which is y dv, plus v dy. Okay, I need to do cleanup. I need to FOIL as well. On the right-hand side, we have a binomial times a binomial, and there are differentials. It's kind of a mess, so I'm just going to go slowly. I'm going to show myself all my steps so I don't mess it up. Okay. On the left-hand side, I have vy cubed dy. On the right-hand side, if I use FOIL, I'm going to go firsts with firsts. And that gives me a y to the fourth dv. All right, I'm going to do the outers with the outer with the outer. And that's going to give me plus y cubed v dy. I'm going to do my inners. So I get a minus v cubed y to the fourth dv. And my lasts gives me minus v to the fourth y cubed dy. Okay, now I want to highlight what is the same, including the sign, what is the same on each side of the equal sign. The vy cubed dy on the right is the same as the y cubed v dy on the left. Sorry, I meant those backwards. Vy cubed dy on the left is the same as the y cubed v dy on the right. Okay, so those are going to go away. If I try to move one over to combine them, I'd end up subtracting from both sides and neither would be left. Now I look at what remains. I see a couple of dv's and a dy. I'm going to move the dy over to the left-hand side. Okay? So the dy is actually a minus v to the fourth y cubed dy. I'm going to add it to the other side, so it becomes positive v to the fourth y cubed dy, and that's equal to, and then I have the two terms with a dv. I'm going to factor out the dv, and I will have a y to the fourth minus v cubed y to the fourth all times dv. Now on the right-hand side, I can see that I have that y to the fourth common to both terms, so I will factor it out. We get v to the fourth y cubed dy is equal to y to the fourth times 1 minus v cubed dv. All right, on the left, I want all y's. On the right, I want all v's. So I need to divide the v to the fourth over to the right, and I need to divide the y to the fourth over to the left. That leaves me with 1 over y on the left. And on the right, I have 1 over v to the fourth minus v cubed over v to the fourth. All of this has a dv. A little bit more simplification, but at this point we can go ahead and slap on our integral symbols and then keep working. On the left, we can integrate. The antiderivative of 1 over y is the natural log of the absolute value of y. On the right, I'm actually integrating a v to the minus 4 minus a 1 over v, just so I see that a little bit more clearly. And that is equal to, remember power rule, you're going to add to the exponent, so the exponent becomes a negative 3, and we divide by that as well. So negative 1/3 v to the minus 3 minus the natural log of the absolute value of v plus c. Okay? All right, let's just rewrite this one more time. So I have the natural log of the absolute value of y is equal to a negative 1 over 3v cubed minus the natural log of the absolute value of v plus c. Okay, now we need to recall. So we recall that x was equal to vy means that v is equal to x over y. So everywhere there's a v, I need to replace it with x over y. Y will stay the same, so I keep the natural log of the absolute value of y. This is equal to a negative 1 over 3 times x cubed over y cubed minus the natural log of the absolute value of x over y, and then a plus c. Okay. Next, that fraction right there, I have a negative 1 over 3 times the x cubed over y cubed. The fraction in the downstairs, we're dividing by that, so we can instead flip and multiply it. The natural logs I would like to combine. So I'm going to move all the logs to the left-hand side, and I'm going to fix that improper fraction. So on the left-hand side, I now have the natural log of the absolute value of y plus the natural log of the absolute value of x over y is equal to negative y cubed over 3x cubed plus c. Now I'm taking this further because I know for certain that this problem in WebAssign requires a nicer written answer. Okay, once the y is all together, it doesn't ask for us to solve for y explicitly, but it would like y to show up in one place. So I want to use log properties right now. If I have a sum of logs, that is equivalent to the log of a product of the things inside. So this becomes the natural log of the absolute value of y times x over y, which hopefully you can see that pretty quickly that those y's are going to cancel. This is equal to a minus y cubed over 3x cubed plus c. I rewrite, I get the natural log of the absolute value of x is equal to minus y cubed over 3x cubed plus c. Okay, a little bit more. Again, I want that y cubed alone. So I'm going to, multiply both sides by a negative 3x cubed. And what ends up happening is negative 3x cubed natural log of the absolute value of x is equal to y cubed minus 3cx cubed. And the last step is for me to add the 3cx cubed to the other side and finally have y cubed is 3cx cubed minus 3x cubed times the natural log of the absolute value of x. And that's it. That's all I can do. Now, if we compare this to our previous answer, it looks like the only difference, they both have a minus 3x cubed natural log of the absolute value of x, but the first time I just got cx cubed, and the second time I got 3cx cubed. Well, the difference between c and 3c is nothing. It just depends on what our initial value is. So we could technically rewrite this because 3c is just c to begin with. It's still just a constant. So we could say, oh, well, y cubed is just simply cx cubed minus 3x cubed natural log of the absolute value of x. But whether we get rid of the 3 or not doesn't really matter. If it makes you feel more comfortable to keep the 3, then go for it. All right, so that's the homogeneous equation problem using the other substitution. Okay, I only have just this one example for homogeneous equations because we do have 2 other methods to learn, but I have worked it both ways so that you can see kind of how things work differently depending on what you choose. The next type of equation is called the Bernoulli equation, and the form of it looks like a linear equation. The reason it is not a linear equation is because on the right-hand side of the equal sign, we have a y raised to a power. So we have the right form. We have dy dx by itself. We have plus p of x times y together. We have equals f of x. But the problem is there's a y raised to a power on the right-hand side. And so this is no longer linear. This is actually nonlinear. And so we have to fix that somehow. And given that it looks almost linear, it is natural to think that whatever we do to fix it will make it linear. And that is true. Okay, so fixing a Bernoulli equation makes it into a linear equation. And so then we're back using the methods of the linear equation section, okay? So two things to remember now. If it's a homogeneous equation, after the substitution, it will be separable. If it is a Bernoulli equation, after the substitution, it will be linear. So what's the substitution? Well, that's right here. We're supposed to identify what the power of y is. Like, let's say it's y cubed. Then I know that the n is equal to 3, and u would be equal to y raised to the 1 minus 3. And then from there, I could solve for y, and I could find dy dx, and I could substitute them in, okay? But the best way to see this is for us to go through the steps, okay? And I want to encourage you to not skip any of the steps as you're going through these problems. It's way too easy to make an algebraic error that you could have totally avoided by just showing yourself all the steps. All right, so I've got my substitution up there. I'm being guided. I need to get this into the supposed look of a linear equation. And that means I need to get it in that standard form. Okay, so we still follow the same steps. Get into standard form. And when we do that, we have dy dx, and then we have a minus 2x over x squared y. So I move that 2xy over at the same time that I divided by the x squared, is equal to 3 over x squared y to the 4th. Let me simplify that once. Dy dx minus 2 over xy is equal to 3 over x squared y to the 4th power, where n is equal to 4. We did also get a domain restriction in there, and I didn't even mention it, but we divided by an x squared, which means x cannot be 0. But we are not being asked for the interval of definition, which is why I didn't mention it before, okay? But I have it in the proper form now, and I can identify that this y to the 4th is actually the problem. It's what's making this problem not linear, and so I need to look very closely at its power of 4 and state n equals 4, okay? Now my second step is we need to get our substitution. Using what we are told up above, u is equal to y raised to the 1 minus n, okay? Where our n is 4, so u is equal to y to the 1 minus 4, which means y to the minus 3, okay? I need to be able to replace the y's in the equation with something in terms of u. I need to replace the dy dx with something in terms of u. So the next thing is to solve for y and calculate dy dx, okay? In u equals y to the negative 3, what I could do to solve for y is raise both sides to a power that ensures that the y will be left standing alone. And so it turns out if I have y to the minus 3 and I raise it to a negative 1/3, power to a power, when you multiply, that simplifies down to just 1. So it looks like I'm going to need to raise both sides of my equation to a negative 1/3, and then I will have, y is equal to u to the negative 1/3. And that's my substitution, okay? I also need dy dx. So I'm going to calculate dy dx, assuming that u is a function of x, okay? So I have a chain rule. I will first apply the power rule for derivatives here. So I get a negative 1/3 u to the negative 1/3 minus 3/3, that'll be a negative 4/3. And then times the derivative of u with respect to x is du dx. Okay? So y is not pretty and dy dx is not pretty, but I promise you when it all simplifies out with the algebra done, it makes everything look pretty good. So I'm leaving at the very top of our screen the original differential equation in standard form, and I'll replace all y's with u to the negative 1/3 and the 1 dy dx with this negative 1/3 u to the negative 4/3 times du dx. Let's do it. So we're going to sub these into the dE. So dy dx gets replaced with a negative 1/3 u to the negative 4/3 du dx minus 2 over x, that stays the same, but the y is now u to the negative 1/3. This is equal to 3 over x squared. The y to the 4th, well, y is u to the negative 1/3, and then that's going to get raised to the 4th power. Okay. All right, let's simplify that just a little bit. There's not a whole lot I can simplify, but looking at that u to the negative 1/3 and then raised to the 4th power, this right here really is just u to the negative 4/3. Power to a power, you multiply. Okay. Now, I want my du dx by itself. I need to get into standard form again. Okay. So that's my next step. Get back into standard form, and we have to figure out what we need to multiply by in order to do that. So we'll get back into standard form by multiplying the dE by, I need to undo a negative 1/3. That means I'll multiply by a negative 3. I need to get rid of a u to the negative 4/3. That means I'll multiply by a u to the positive 4/3. And that should take care of how ugly this is, okay? So I've got my negative 3 u to the positive 4/3, and that's going to multiply into this negative 1/3 u to the negative 4/3 du dx minus 2 over x u to the negative 1/3 equals 3 over x squared u to the negative 4/3. When this hits the first term, the negative 3 with the negative 1/3 is just 1. The u to the 4/3 times u to the minus 4/3, that's just u to the 0, which is 1. So I leave behind du dx when I distribute. When it distributes to the second term, I have that minus 2x already, 2 over x already. That becomes plus 6 over x. And then the u becomes u to the 4/3 minus 1/3. I'm just going to show the steps so it's very clear why things simplify the way they do. Equals, when that minus 3u to the 4/3 hits the last term, the minus 3 and the positive 3 become a minus 9 over the x squared, and then I have the u to the 4/3 times the u to the negative 4/3, which is u to the 0, and that's 1. So the only thing left for us to simplify is the u to the 4/3 minus 1/3. Well, 4/3 minus 1/3 is 3/3, which is just 1. Okay, so it's just u at that point. And this right here, this is a linear equation. And we know how to solve that. Might not be our favorite thing to solve, but we know how to solve it, okay? It's in standard form already, so the next thing we need to do is get an integrating factor. And if you recall, the integrating factor is mu of x is equal to e to the integral of p of x dx. Okay, our p of x with its sign is just 6 over x. So mu of x is e to the integral of 6 over x dx, which gives us e to the 6 natural log of the absolute value of x, which needs to be rewritten as e to the ln of x to the 6th power, and then the e and the ln undo each other, and this leaves behind x to the 6th power. Okay. Next step, hold on one moment while I shrink everything up a little bit so that I can fit my work in. We're almost done. Okay. So the next step is to multiply the integrating factor through the linear equation. So we're going to multiply mu of x equals x to the 6th through the linear equation. So we get x to the 6th du dx plus, when I send the x to the 6th to the 6 over x, that becomes 6x to the 5th times u equals minus 9x to the 4th after the x to the 6th simplifies with the x squared. On the left-hand side, we need to recognize that this is d dx of x to the 6th times y. Right? If we were to take the derivative of x to the 6th y, we would get 6x to the 5th, I'm sorry, not y, u, I'm in the wrong variable. If I took the derivative of x to the 6th u, it would be a product rule. I'd get 6x to the 5th times u plus x to the 6th du dx. So that works. On the right-hand side, I just have my minus 9x to the 4th. And now I can integrate. So I integrate with respect to x. So I'm integrating d dx of x to the 6th u dx. That's equal to the integral of minus 9x to the 4th dx. On the left, the fundamental theorem of calculus takes care of us. And then we have x to the 6th u is equal to minus 9 over 5x to the 5th plus c. And then we need to finish this off, divide both sides by x to the 6th, and then u is equal to negative 9 fifths times 1 over x plus c over x to the 6th. Now, I have to remember something. We need to recall that u was not the variable we started in, and u, going all the way back up, u is equal to y to the minus 3. So I'm going to replace it. I get y to the minus 3 is equal to, and I'm going to rewrite my fractions a little bit. I have a negative 9 over 5x plus c over x to the 6th power. And I'm going to leave it like that. If I want to use, well, maybe I should go a little bit further just to show the algebra. If I want to rewrite this as 1 over y cubed and then solve for y cubed here somehow, I need the right-hand side to have a common denominator and be added and just be one fraction. And a common denominator would be 5x to the 6th. So the first fraction is missing 5 x's, so an x to the 5th. So I need a negative 9x to the 5th. And the c is just missing a 5, so I could write that as 5c. And then I have 5x to the 6th in the denominator. Okay? So then if I want to solve for y, y would be equal to, if I raise both sides to a negative 1/3 power, it'd be equal to a negative 9x to the 5th plus 5c over 5x to the 6th raised to the negative 1/3 power. And that negative exponent can be made positive by flipping the fraction that's inside. So this would be equal to 5x to the 6th over negative 9x to the 5th plus 5c, all raised to the positive 1/3 power. I don't know if that's taking it too far. We were not asked for an explicit solution, so keeping it as y to the minus 3 would probably be okay. But if you were asked for an explicit solution, you would need to go through this process. Okay, so it's there if you need it. All right, that is the Bernoulli equation method. There are a lot of steps to it. I would say write down the steps in your own words so that you're very clear on what you need to do every time you're told to solve the Bernoulli equation. Okay? The next method is called the reduction to separation of variables. This method is going to require us to recognize that there's something linear in our differential equation. And what I mean by linear is the old-fashioned linear, like college algebra linear, like y equals mx plus b sort of linear. In other words, we will see combinations of x and y without any powers. Or, no powers. Well, like we would see like ax plus by plus c somewhere where b can't be 0, a could be 0, and c could be 0. But the point is we're seeing like this linear expression in terms of x's and y's, and it's making it impossible for our equation to be linear or separable. And the point of the reduction to separation of variables is hopefully very clear in the title. We are going to use a substitution that reduces our equation to a separation of variables problem. Yay! So homogeneous methods bring us to a separable equation, and so does the reduction to separation of variables. Once we recognize the linear part in our differential equation, we are going to let u be that linear part. Then we're going to calculate du dx, keeping in mind that x is just x and y is a function of x. Okay, so we'll calculate du dx, and then we'll have to solve for dy dx in the du dx equation. So we'll solve for dy dx to sub into the differential equation. Okay, and I guess I say that right below. And then we'll have a separable equation. So let's see how that works. In this particular problem, we're told to use the reduction to separation of variables method to solve the DE. In your homework in WebAssign, I believe they don't really give it a name. They just say use a substitution, and they kind of make a hint towards it being a function of ax plus by plus c, and so then you have to remember. On an exam that I write, I will use the words, use the reduction to separation of variables, because that's its name. All right, so I'm looking at my equation. dy dx equals 2 plus the square root of y minus 2x plus 3. Okay, I want to recognize where there is a linear expression in terms of y and x, and it is underneath that radical. The whole thing, y minus 2x plus 3, that's a linear equation. Okay, so I'm going to let that be my u. Okay, so first, let u equal y minus 2x plus 3. Second, we're going to calculate du dx and solve for dy dx. So du dx is going to equal, the derivative of y with respect to x is just dy dx, and the derivative of minus 2 with respect to x is just minus 2. Okay, so that's du dx. Now we'll solve for dy dx, and dy dx will just simply be du dx plus 2. All we had to do was move a 2 over, and they're generally pretty straightforward like this. Okay, so we have our perfect substitutions that we can put in. They are, we'll replace the y minus 2x plus 3 with a u, and we'll replace dy dx with du dx plus 2. All right, so let's go ahead and substitute everything in the dE. dy dx is du dx plus 2 equals 2 plus the square root of u. The 2's on either side of the equal sign have the same sign, so if I was to move one over to combine it with the other, they would both go away because I'm subtracting 2. So this simplifies to be du dx is equal to u to the 1/2 power. I'm kind of getting things ready. And this is separable. And that's what we want. That's great. So I need to move the u to the 1/2 to the other side and move the dx over as well. So this becomes 1 over u to the 1/2 du is equal to dx. I can rewrite the u to the 1/2 as u to the negative 1/2 du is equal to dx. Okay, now I've substituted everything in and I have simplified it. Now I can integrate. So the integral of u to the minus 1/2 du equals the integral of dx. On the left, we use the power rule. Negative 1/2 plus 1 is a positive 1/2. And so we're going to divide by positive 1/2 as well. U to the 1/2 over 1/2 is equal to x plus c, since on the right we're just integrating a 1. This means that 2 square root of u is equal to x plus c. But now, whoops, I'm going to go back up here, draw a little squiggle line. Step 5 is to recall that u is equal to, let's get it there, y minus 2x plus 3. So we need to go into our solution and replace the u with the y minus 2x plus 3. So we get 2 square root, and instead of u, we put in y minus 2x plus 3. And then on the right-hand side, it's still just x plus c. And I would leave it like this, okay? The question does not ask for an explicit solution, so I don't want to square both sides and have the chance of misconstruing my answer because y is under a square root. That was part of the question and it's part of the answer. I'm going to leave it like this. This is the purest answer I can give. Okay? So that's the method of reduction to separation of variables. Just to recall, today we covered the homogeneous equation, which reduces to a separable equation. We covered the Bernoulli equation, which reduces to a linear equation. And we covered the reduction to separation of variables, which clearly reduces to a separation of variables problem. Please reach out if you have any questions at all.